All right, we come to the next section in Chapter 7, and this is called the law of cosines. So now the first question is, why do we need a law of sines and a law of cosines? Well, the law of cosines is used initially. It's the first step if we cannot use the law of sines. So when are those two steps? Well, those two steps are when you have two sides and the angle that is couched between them. The other part is just so you know three sides. If you know three sides, there's no way to use the law of sines, because law of sines is based upon the fact of having some knowledge of the relationship between the angles and the length of the other side. So it's just the first step that we use. All right, so the law of sines, what does it look like? There it is. There's all three variations of it based upon the side that you don't know. So if you don't know side A, you would use this one. And notice it's really just the Pythagorean theorem all over again. Look at that. Is that Pythagorean theorem right there? With the extra piece being the product, or the doubling of the product between the two known sides multiplied by the cosine of the angle. So really, in a sense, Pythagorean theorem minus this piece here allows us to derive any opposite side of the angle, not just the hypotenuse. All right, so in English, that's what it says right here. Read it if you like. There it is. All right, the derivation of it here, this is from the textbook here. Not going to spend too much time here, but technically what we have is we are moving this off of a right triangle, still keeping the whole concept of right triangle based upon angles that we know. So if you move this out to the right of the y-axis or to the left of the y-axis, you can still derive the same exact conclusion about what A is based upon angle measurements. And so based upon that, we derive our formula. All right, so how do we use this? Well, two different stages, like I told you. There's two different times we can't use the law of sines directly. And so the first one is SAS, so side angle side issue. Can't use the law of sines, therefore we're going to use the law of cosines. But once you do that, once you find the opposite side, we go back and start using the law of sines right away, because that's so much easier to do and a lot shorter. And then in order to figure out the next angle, we just use the sum angle formula. Let's do one practice problem. All right, let's start it. So practice problem, we have a triangle. We know the C value, the A value, and the B value. So we know the two sides and the angle in the middle. Let's draw this out here. So labeling our triangle, A, B, and C. It doesn't really matter which way you label it here. Normally it's written counterclockwise, but it doesn't really matter as long as we set up our values where they should be. So this would be 60 degrees here. I know that to be 25 because that's a little c value. Little a value is 15, and let's go for it here. So notice I can't use the law of sines. I don't know the corresponding angle measurement and its opposite side, so therefore the law of cosines helps us out in this area. And so I'm going to label this as B, and then the formula that we want to use is this one right here. Since we don't know what the B value is, we're going to plug it into this formula right here. All right, and two ways you can do it. You can, well, actually no. You can move the formula around whichever way you want, or you can just plug in values and keep on going here. I'd rather just plug in the values here, keep on going here. So C is 25 squared. I plug in the 15 squared, and then I go 2 times 25 and 15. And then cosine of what I know, cosine of 60 degrees. All right, if you punch this into a calculator right away, like a TI-83 or something like that, that would probably be the best way to do it, because the TI-83 calculator and any of the larger TI calculators, they actually will keep the order of operations in sync. So notice you have exponents there, you have subtraction, you have multiplication. So on the higher bit calculators, the graphing calculators, they do understand order of operations. If you don't have one of those calculators, then you got to think about, you got to do the order of operations yourself. So you're going to have to do exponents first, then you have to do the multiplication, and then you have to take the cosine of 60, then subtract it from the addition of those two. A lot of more work here. So what I did it the easy way. I plugged it into a TI-83 calculator, and I got an answer of 475. Now that is not the answer yet, because I have to take the square root of both sides, because I'm dealing with a unit length value, I know it can't be negative, so I'm only going to take the positive value. So 21.8 inches, that's what we have here. Okay, once we get that, once we know it's 21.8 inches, now from here on out I can use the law of sines, because now I have, or I know the angle and its opposite side right there. Perfect. Let's use the law of sines. Law of sines is sine of 60 degrees over 21.8 is equal to sine of, now we've got to choose. Do we want to do the A angle first or the C angle? It doesn't really matter as long as you correspond it correctly here. So sine of A goes to 15. All right, from here, let's see. I'm going to, looks like I multiply both sides by 15. I'm going to take the sine inverse of that because I want the angle value. So multiply 15 on both sides. Sine inverse of this. Plug that into a calculator. Hopefully you know how to plug that in based upon what we have done in the previous section. And voila. How about a 36.6 degrees as you round it to the nearest tenth? Okay, now the numbers could be just slightly off sometimes. You may be off by a tenth just because your measurement values are not precisely precise. So be careful, kind of be mindful of that. It's 21.8. If it was 29.89, that might change this to 36.7. So just kind of be mindful of the fact that it could be off just by a little bit, and that's what you're off by. Okay, so if we know angle A now to be 36.6, I could do law of sines for angle C, but even easier. If I already know two of the angles inside a triangle, all I really got to do is figure out what is needed to get to 180. So in this case, this is 96.6. I'm going to take that away from 180, and I got what I need here, which is 83.4 degrees. So that's an answer, that's an answer, and that's the answer for the missing parts of my triangle. All right, let's do a application of this stuff here. Where is this used at? Well, it's used at navigation. A lot of navigation stuff is used with law of cosines, just because you have sort of cross winds. You might even have cross currents that are crossing a barge or a aircraft carrier. So you need law of cosines then. The other one is, which is right here, it's the whole concept of flying. If you're flying, bearing a certain, having a certain bearing, going somewhere, you can figure out the distance between things here as we do this right here. So suppose that a Boeing 747 flying over Disney World headed due south at 552 miles per hour. That's cool. 20 minutes later, F-16 passes over it, but it's going north, which at that speed. So now the question is this: find the distance between the airplanes after 3 hours if they kept their same distance. Let's set it up here. What would it look like? Well, a few things here we should note is from D, we have the 747 headed south, due south from our origin. All right, 20 minutes later, you have the jet flying over. So because of 20 minutes later, we're going to correspond everything to the jet time. So therefore, we have to add extra little time to the 747 here. All right, so looks like we know the angle measurement here, which is 37, and it looks like this should add up to 180, right, if you went all the way around. So therefore, this is a supplementary angle of 143 degrees. And let's see what we have here. We know the side, we know angle, side, and so that means I can figure out the distance, that little d value right there. All right, how do you do it? Plug it all in. There it is. The only change I would probably make, if you know the time value, just put in the time value so you don't have to put in t later. So if you know t is already 3, instead of multiplying everything out and actually doing a binomial factor here and squaring that, oh, that's too much work. I would plug in the t earlier, so then I got t plus 1/3 already, and then I can work with the decimal approximations there. So our problem, let's see, repeat example 2, assuming that the F-16 is traveling at a speed of 1375 with that kind of a bearing, and then the Boeing 747 is traveling south, also with its own bearing. That changes up the problem a little bit here. Let's draw it out. Let's see what we get to here. Drawing it out, I got my F16 nicely traveling, that bearing, and that speed right there. I'm going to put it as T here because that's we're going to base all our travels based upon the time the F16 passed. There's my bearing for let's see, was it the 747, adding on an extra 20 minutes here. And that's what I'm trying to find, that red line right there. So my first question is, what's the angle right here? What's the angle between them? Well, let's see. I think we got to figure this out. The small angle here, getting back to the x-axis, that would be 15, because 75 plus 15 gets you 90. We also know that whole piece is going to be 90 there, and then also the bearing of the 747 is off by 12 degrees, so all that added together, 15 plus 12 plus 90 should give us the angle measurement of that big angle inside there, which is 117. Once I know that, I'm good to go. So let's go for it here. So in 3 hours, and this is what I said on the previous problem here, you know what I'll do? I'm going to figure out my values before I start plugging in, because I sure don't want to plug in t values into mine. So if the jet is traveling 1375 for 3 hours, it has covered 4,125 miles. And if the let's see, 747 is traveling that way, it has covered a certain amount of miles as well. And let's see what we got here. So again, big numbers here. I would really encourage you just to use a TI-83 calculator, something that would do order of operations already, except if not, then this is going to become really a big problem to solve here. Punching all that into a calculator, don't forget it's d squared, so I just put that in here. And I'm going to get a big humongous number, and then don't forget you're still going to have to take the square root of that number, whatever you get on the calculator here, and with that I get 5,219.5 miles. That is the distance that the two airplanes are separated by. Cool. Alright, the other time that you would use the law of cosines first is if you know all sides of a triangle, but you don't know any of the angles. So we need at least one angle to establish proportionality first. So practice problem number 3. I know that A is 4.5. Let me draw my little triangle here first. This is normally how you label a triangle, ABC. It goes counterclockwise, starting with A. Don't have to always do it that way, but that's usually what we do. All right, 4.5 for A. I got a B of 6.7. I got 5.3. So let's go for it here. Pick whichever one you want. You can actually find A, B, or C. Normally what we do, because sometimes you can get into angle measurements that don't make sense. Here's a trick of the trade. The book doesn't talk about it, but I'll talk about it here. If you know all sides of a triangle, you always pick the biggest side as your sorry, I'm going ahead of myself here. As the one that you want to solve for. Now notice here we're not solving for the B value. We actually are solving for the angle value. And so what we have to do now is we have to move everything around. We're solving for the B value. That's why this is so much different here. You're going to move the C squared to the other side. Move the A squared to the other side. All right. And then I want to show it to you in this 2 steps here so it doesn't look that bad here. All right, then what we're going to do is we're going to divide. So what I want to do is I want to technically solve for my angle. Divide both sides by negative 2CA. And that's still not done because I'm not solved for B yet. I've solved for cosine of B. So let me move things around. First things first, I'm going to change all my signs around. Okay, I don't like negative 2 on the bottom of my fraction. So I'm going to move the negative to the top. So the C value becomes positive. The A value becomes positive. The B value is the one that goes negative. So and then on the bottom, I have a positive 2 now. All right, one more. Let's plug this in here. One more term before we start plugging in here. We take the cosine inverse, and then we start plugging in. Oof, okay, there's all my values there. Again, I encourage you guys to use a scientific or graphing calculator that can do all these steps, do as order of operations, or else it just becomes crazy. All right, plug in that in. The only thing is that also you got to be mindful of, make sure you are in degree mode of your calculator. There's two different modes you can be on. If it says RAD, that means you are in radian mode. If it says DEG, that means you're in degree mode. You want to be in that one. And punching all that stuff in, cosine inverse, that's what I have on my calculator right there. As I punched it in, it looks kind of strange at first, but it's cosine inverse of all that stuff in there divided by, and notice I needed extra parenthesis for the bottom. Careful that you need an extra parenthesis for the top, because you want to hold the numerator as one big giant piece, and then you hold the denominator as one big giant piece. So yes, you do need extra parentheses on there. Try it by yourself on the calculator, but you should get at 85.9 degrees to the nearest tenth. Cool. With that, now the question is, now can we do the law of sines? Absolutely. Because we know now we have a correspondence between a angle and its opposite side. Then we're going to find out another angle. All right, let me just draw what we know already. We have that already initially, and now we know 85.9 to be right there. And now let's start the law of sines, because that's what's going to help us here. All right, the angle that I just figured out over its opposite side, and then just choose sine of C or sine of A, whichever one you want to do. I'm going to choose sine of A, so I'm going to multiply both sides by 4.5 to solve for sine of A. So multiplying by 4.5, and let's scoot the sine of A to the left-hand side. So essentially, I multiplied both sides by 4.5. All right, and then now I have to take the sine inverse of that. So sine inverse of 4.5 sine of 85.9 over 6.7. And again, on a calculator here, you got to punch all that in. Make sure I have a 42.0 if you round it off to the nearest tenth of a degree. Got that down, and I think the rest we should know. Since I know this one, I know two angles of a triangle. I'm going to add those two up, subtract from 180, and we are good. That should be 127.9. So therefore, if you subtract it from 180, that should give you a 52.1. There it is. Solved all of it. Solved for all three angles. Practice problem number 4 has one little issue here with this whole concept of side, side, side. If you were to make a little triangle, here it is, labeling ABC, putting in all the sides here, I got 2, I got a 3, and a 6. Now, if you know your geometry well, you will see that there's a little problem here. Hey, there's a problem. Hey, that doesn't make sense. If you don't know it, that's okay. Let's still keep on through. So let's go with what is the longest side we see? Oh, 6. 6 is the longest side. So the formula that we want to use involves c squared as being the one that we solve for. So what I want to do, and kind of just draw it out again. Here's what I know. I know because the length of that side, 6 would be the opposite of the biggest angle that we have. That's why I just kind of redrew it. Notice that the first triangle that I drew, it seems like everything it's an acute triangle. And I'm going to show you, no, it's not an acute triangle. It's actually an obtuse triangle. You know it's obtuse because just the bigness of the 6 compared to the 2 and the 3. All right, punching it in. Let's see what we get. It looked kind of weird at first here. Let's go for it. Here's a formula that I'm going to use. Now I'm going to solve for my angle, right? So I'm going to move the A, I'm going to move the B, just like we did last time here. Leave the negative 2AB cosine C on one side, divide through by a negative 2AB, and just like we did on the previous one, I'm going to change all the signs around. So cosine of C becomes positive A, positive b and a minus c squared. So I just changed all the signs so I can have a positive 2ab on the bottom. Now, do you have to do that? You don't. You can plug it all in, but just don't forget the negative on the bottom. All right, still not done because we're trying to solve for the angle. So really what we're going to punch into the calculator is a cosine inverse of all that stuff. So as you punch it in, the 2 goes in as the a value, 3 goes in as the b value, 6 goes in as the c value, and then at that point, make sure again you are in degree mode. And if you do that, your calculator most likely will say error, or it'll say domain error. So now the question is, what happened there? Why is it doing that? What's the domain error all about? All right, so let's go for it here. So this triangle that I drew up here, it actually is not very accurate. It's a very rough sketch, but it's actually not even a true sketch, because this is what's really happening. If you have a side of 2 and a side of 3 on a triangle, notice the two small sides, if you add them together, they only add up to give you 5, not 6. And 6 is what you need to get to the other side. So comparatively speaking, here's what happens. The two sides are shorter than the third side all put together. So therefore there's a gap. Therefore this is not even going to make a triangle for us. So right here, there's no triangle. So answer to this, pretty much it just means no solution. There's no solution to this triangle, and there it is. We can just write no solution right there. All right, and that is it for 7.2.